ocasión tenemos al doctor Xu Hong de la Universidad de Griffith en Australia, que nos va a presentar su plática acerca de la dinámica de la materia orgánica del suelo y ciclo de nitrógeno en ecosistemas forestales nativos de Australia subtropical. Una visión general de poquito tiempo, nada más 30 años, de una serie de estudios sobre la quema prescrita y la deposición de nitrógeno en un escenario de cambio climático. Él es profesor de sistemas en suelo, planta, clima en el Centro para la Salud Planetaria y Seguridad Alimentaria y la Escuela de Medio Ambiente y Ciencias. Ha publicado 400 artículos y manuscritos en conferencias, de los cuales 340 han sido en revistas arbitradas y es autor de 2 libros. Ha investigado extensamente en procesos biogeoquímicos del carbono, nutrientes de los ecosistemas terrestres, en ecosistemas agrícolas, agroforestales y forestales en Australia, China, Europa y Estados Unidos, y se ha desempeñado como presidente del Grupo de Trabajo sobre Suelos Forestales en la Unión Internacional de las Ciencias del Suelo. Es editor en jefe de la revista Journal of Soil and Sediments, editor en la revista Environment Science Contamination and Restoration, editor coordinador en Environmental Geoquímica, Health, y es miembro del Consejo Editorial Pedosphere. Entonces, gracias a él también tenemos este número especial que todavía están a tiempo de mandar sus publicaciones y tenemos hasta el 15 de agosto para tener nuestro special issue relacionado con esta primer conferencia internacional sobre sustentabilidad e innovación del suelo en el marco del 47 Congreso Mexicano de las Ciencias del Suelo. Y entonces le vamos a dar la palabra al profesor doctor Xu Hong.
Very much. I don't.
No, we're going to need it for virtual presentation.
Okay, all right. I see. Well, good morning, and this is a great opportunity for me to be here, and the first time to visit Mexico City, and it's a city of attraction and imagination. So I think I'm very happy to be here. And I also apologize that I missed the transit from Los Angeles to Mexico City, because Australia generally, to visit the US, it's a fee visa waiver. So you just need it online registered, a couple hours. But I saw the transit don't need a visa, just pass. And apparently American insist I must have a called visa waiver registered online. So I have missed the flight. So apologize. I wish I could deliver the presentation yesterday morning. Now, what I do is I also want to ask you to bear with me, because my English probably is very much Australia. It's quite different from the American English. And my American colleagues sometimes find this difficulty. So I hope I speak a bit slow with PowerPoints, and hopefully you can follow what I'm trying to say. Well, the talk which I'm going to give to you is over the last 30 years. So many PhD students, even including Dr. Fred Riverson, the work. So it's many postdoc PhD student work over the last 30 years. So before I go into detail on that presentation, but I also want to share with you that some background or context that is why we're interested in prescribed burning or fuel reduction burning in Australia. And so this picture, this diagram, which is I present here, represented 2 major studies which I've undertaken in the last 20 years. The first one is this part. Okay, that is about 18 years work. And I did calling the tree rings, the big trees. In Mexico, there's many big trees. And I also collaborated with my Mexico colleague, Amanda. So we collaborate. So we're calling trees globally. and then just looking at how the trees are responding the real climate change, okay, in the last 150 years or 200 years. So that work, initially, actually, I went to France to attending an international forest soil conference in Bordeaux, which is, I think, for many people, I think Fred would know. Many people would know it's a winemaking area. Bordeaux red wine is very well known. And we went there, the international conference. The host is very, very serious and enthusiastic. So they provide advice from the lunch, evenings, every day. And it certainly stimulated a lot of discussions. And during that talk, there's one Belgian colleague give you a presentation. They say the acid deposition in the last 150 years, its impact on the calcium, magnesium nutrition of European trees, particularly beech and oak. So that study demonstrated in the last 150 years, there's a significant impact of acid deposition. So it's compared with the central Brussels and with the rural area of Brussels. So that means you can look at the acid gradient. And he published that work in the Global Change in Biology, which is a very new journal then, to 2004, 2000, yeah. And after drinks, and I said, now you finish all the study. Can I have all your tree rings? Because I said, I'm interested in climate change, not just the acid, I'm interested in how CO2, carbon dioxide, temperature, rainfall change, how they impact on tree growth and the feedback to the climate change. They said, oh, it's all yours. So they shift all the samples to my lab, and then my postdoc, Dr. Tim Blanfield, my colleague, and did all the carbon isotope composition, C13, and try to understand not just growth and what the drivers of the growth. For example, is that due to water use efficiency, which is a photosynthesis divided by semiconductors, which is the environment, or due to acid deposition, or due to artifacts. So I'm basically using, because in Brussels they have more than 200 years rainfall data, and they have more than 100 years temperature data. And because I'm interested in, most of tree ring research is using tree ring to reconstruct past climate, rainfall, temperature, using the linear positive relationship with temperature, with rainfall. And but recently we noticed that the past climate change is quite different from recent climate change. In the past, it's natural. It's a very slow process. For example, that the climate change takes more than 10,000 years or even longer. So you can see the temperature and the rainfall are coupled. But the recent climate change, we know that the CO2 is going very fast. Instead of 10,000 years, which is increasing about 200, 300, or 400 ppm, but in 150 years, it's increased now to about 140 ppm by now. So that means very fast compared with the historical. But most important, I think we know that most of the natural system, ecosystem, or complex system with many drivers, they usually would expect the system response be non-linear, not linear. Linear means the previous, they use the tree ring to reconstruct temperature, rainfall is using linear relationship. That could be true when change is very slow. But when change is very fast, that could be non-linear. Okay, so my hypothesis at that time is using this data to test if using real tree ring data, see if we can look at the climate change. Okay, so what we do is, I've done the carbon isotope, I've done the M15, I've done the oxygen 18. Carbon isotope is a unit as an index of water use efficiency. That means organic matter, dry matter production per unit of water consumed. Okay, so, but it's a ratio. By measuring M15, so we know the acid deposition, but we also know nitrogen. If chlorophyll, if nitrogen, photosynthesis is driving the system, We also measure oxygen 16, 18. That means that we also look at the water, the many somato transpiration, so we can differentiate. So that is a very interesting study. After about 2 years work, my colleague, Dr. Tim Flaunfield, and my Belgian colleague, we found some very exciting studies, but I'm not going to show you the details because I just want to give you background. And so you know, the climate change can be quite severe and real. So the results showing is, CO2 increasing. We do see the tree growth increasing initially. Okay, it's linear, it's non-linear, and as CO2 continuing rising, we find the tree growth start plateauing. So it's like when you throw a stone, gravity will pull the stone up, but its gravity is the one pulling down. But in this case, what we found is water, because the photosynthesis is the CO2 and the water, both substrate. Whichever substrate is driving is the limiting factor, and the growth photosynthesis will be controlled by the limiting one. Okay, so what we found, CO2 initially is limiting, water is not that limiting. So CO2 increasing tree growth, which is expected, which is all the short-term experiment indicate CO2 fertilization effect. But it's reached tipping point, and in Brussels, it's about the 1960. So what means beech oak trees in Brussels maximize the carbon uptake every year. Once they pass the tipping point, the more CO2, the less growth, because it's not CO2 is poisonous. It is because CO2 increases temperature driving water reduction. Okay, so that means water is become limiting. So CO2, water is continuing intact. So that pollution gradient is also the rainfall gradient, because the Brussels very polluted area, they have a high acid deposition. They also low sea level, and in Brussels, it's about 80 meters above sea level. The mean annual temperature over the last 150 years is about 12 degrees on annual. And the annual rainfall is about 800 millimeter rainfall. Whereas another remote area, which is no pollution, is high Belgium, and it's 120 meters above zero. That means that it's about 40 meters higher than Brussels, but the rainfall is significantly higher. It's 1,200 compared with 800. And the temperature is lower, which is about 10 degrees. So you can see the pollution gradient, it's also rainfall gradient, temperature rainfall gradient. And in Brussels, the individual trees group by them together. So that means that we got 3 sides, beech, oak, beech, they're all nonlinear increase. Okay. And in the high Belgium, because the trees growing side by side, so we can look at the split effect on, and what we found in 1972, 330 ppm, the less water limiting environment also tipping over. It's about 50 years ago. So what that means, in Brussels, 60 years ago, the trees each year will take less CO2. If the CO2 emission is constant or even zero, the forest system is give a positive feedback to CO2 in the air. Okay. In the high Belgium, it's about 12 years later. So what we found is in that specific areas, annual rainfall is not changing. Annual temperature, every temperature is increasing, okay, with CO2. So what we found is as the annual mean temperature, the seasonal mean temperature, summer rainfall, summer temperature, or growing seasonal rainfall, growing season temperature increasing, the ground seasonal rainfall is declining. So temperature going up, rainfall going down. So you don't need to be Einstein to figure out it's a matter of time, water will become limited. Evaporation is increasing, precipitation is decreasing. That explains the Brussels result. We're very, very excited. And because the challenge is the traditional, the tree ring theory. And then my colleagues and myself were very excited. So we sent to submit to Nature because it's a challenge of the traditional theory. And we wait for 3 or 4, probably 5 weeks, no response. We said, well, because usually they send the sorry letter very quickly, usually about 1 or 2 weeks. Sorry, this is been rejected. So after about 5 weeks, we received a letter from Nature editor saying, oh, we find your results interesting, but we don't know your methodology, technical background, or analysis are sound. So we need to send out for review. So they send out for experts for review. But you know that 80% Nature submission was rejected straight away. My first submission to Nature 2000 was straight rejected in 1 week. It just straight away. So we are very happy, but we know that most of submission to Nature still rejected. So it just at least we sort of give it another try. So after 7 weeks, the Nature review coming back. There's 2 reviewers. One review is treating experts, because I'm not treating experts. And he published 1 paper in 1998 articles, which is as I said, I'm only following Nature in 2000. Before that, I don't follow every issue in Nature. So I missed his article, didn't read his article. He's very unhappy because I challenged his theory, because his theory is linear increase, temperature, and then a lot of that, and many trees globally. He's very, very unhappy. So he gave me a very hard time. He said that these people just have 30, 40 trees in Belgium. The data, particularly most recent data showing declining, it's very preliminary. It's probably location specific, not a global phenomenon. So he makes a lot of lists. So, but the other reviewer is probably more physiologist. He said that he liked this one, but he said there's no climate change model indicate warming will result in the water limitation in 2007. There's no model say warmer and water limitation is the same. The second thing is that if you can prove this one is global, if this one is global phenomenon, that could be potentially Nature cover story, but you need to do more work. It's probably just location specific. So after a while, so in the last 16 years, so we're doing tree rings everywhere, just try to prove if I'm wrong or correct. So recently, because I stepped down, I also involved as a research institute director for 16 years. It's a big group. More than 200 people, so I also have a big responsibility to manage people. So once I stepped down, I have a lot of time to look at research. So we summarized the global data. For the last 18 years, the results is as such. The first forest biome past tipping point is tropical. I said it's about because there's a range, everywhere got a range, about 1956 year, 56. So long time ago, tropical forest is potentially a source, not a sink. And the last one past tipping point is Bora forest, which is a very cold area, like Alaska and Sweden, northern Sweden, and the northern China, 1997. So that means about 20 years ago, 25 years ago. And then when I do the total summary, global forest tipping points is 353.4 ppm. So that is 1990. So that means, some work is published, some work is not published. Mostly it's not published. Indicate the forest globally past tipping point. About 30 years ago. So the forest, we hope a big sink, but relatively since the last 30 years, the ability to take CO2 is diminished. So that what means the carbon, the forest ecosystem carbon feedback to climate change or to CO2 is positive. That's why the warming is accelerated. Even the emission is zero, but emission is not the zero, it's going up too. So that means if you notice that recently there's a clear change in of terminology on climate change from global to global boiling. So that means the temperature is increasing much faster. So that is the background. Carbon cycle, unfortunately, most forests past tipping point. And my work is empiric, but in 2009, there's one Nature models results about more than 1,000 climate change scientists and the soil scientists, ecologists globally. They work out 7 planetary boundaries, which is the Earth's planetary boundary. The first one is carbon dioxide. This is theoretical, is 350 ppm. And nobody believes it. What that means is the theory. But my work showing forest is very similar to that. So what that means, perhaps most of the carbon in the Earth, on the Earth, probably is in forest. Others is less changing. It's not that big thing. No. So, and the other thing is, if you think about the experiment have 1% error, because I'm an experiment, 354 ppm, 350 is the same. So what that means, from theory, from experiment indicate force globally probably not play the carbon sink role relatively compared with what we like to see. Okay, so that means climate change is accelerated. Warming will be much faster. In the last 10 years, so that one yet to be published. Hopefully in the next 3 to 4 months, I'll summarize, submit. And the next one is carbon nitrogen cycle. What we found, not just carbon cycles past tipping points, the trilling work, plus the meta-analysis they published in ecology, nature ecology and evolution. But my work is trilling work, indicate global forest, nitrogen cycle also past tipping point. Okay, that means it's not just water is limiting, nitrogen is also limiting. And but again, that work yet to be published. And that meta-analysis is statistic. They find that it's not just forest, but most of the data come from forest. They found global terrestrial ecosystem, nitrogen is become limiting. So that means it's same to my trilling work. But that the meta-analysis is different from trilling because it's experimental. Meta is just synthesis. So what that means, nitrogen is also limited. So the carbon and the nitrogen cycling is going wrong way. Okay. So now, I think probably talked too long for this one. But this is about 20 years work. So it's easy to draw the graph, but very hard to prove. Computer is problem. Okay, yes, there is. Right, I think let's stop there. Now I'm on fire. Okay. So the reason is because climate change is really going mad. Okay. Summarize the work which are in the tree rings. When you need the rain, rain is not there. Where you need the rain, rain is not there. When you don't need the rain, rain is there. Where you don't need the rain, rain is there. It's very unnatural. So that is a key feature of human footprint, unnatural. I mean, fire is associated with extreme weather. The other thing, I think you probably noticed that climate extremes, drought, flood, wildfires, that are closely associated with climate change because too much energy. When you have a lot of energy, so they're driving the water into the vapor for a long time, no rainfall. And then when the cold front come in, all the water just drop in like fresh flooding. Okay, so my treating work also indicate the intensity and the frequency of drought, flood, and the fires are increased as climate change intensifies. So that means we need to treat fire more seriously. Okay, thank you. Next one. So it just shows you the fire can be very devastating. Next one, please. It's all about the fires. Yep, next one. So some of the fires are from California. Some of the fires from Australia, because Australia also has big wildfires. Next one, please. Yes, please. And next one, please. Now, this is why Australia is doing fuel reduction burning, because in urban forests, we try to prevent wildfire, because once the urban, if you don't burn the little floor, when the weather, the wildfire coming, they'll not just wipe out big forests, they also wipe out a lot of residential area. So in Australia, most eucalypt forest is fire tolerant. It means in the winter, if you burn the fuels, it's reduced fire hazard. Okay, so this is a typical fuel reduction burning. So in the winter, we don't burn in the summer. Okay, in the winter, low temperature in the evening, and then, but the question is how frequent we can burn without degrade ecosystem and about diversity. Okay, so next one, please. And prescribed burn, you will find the big trees are survived, but understory, little floor, burn. Next one, please. Okay, the first firework start with my first PhD student, Dr. Danny Guindo from Philippines. So they are in two different forests, the dry forest and wet scleral forest, which is eucalypt dominant. Yeah, next one, please. Okay, so we've done a lot of work from the PhD using NMR, using also the stable isotope, look at the biological nitrogen fixation, because when you, after fire, a lot of understory legume will regenerate. And we need to understand how much legume can help us recover the carbon, recover the nitrogen, because when you burn, you lose some carbon, you lose nitrogen. Okay, next one, please. And also we're looking at nutrition aspect too. See if you burn too frequently, would that you could become nutrient limiting. Okay, and so we're using some fertilizer experiment to test burning effect. The burning region usually burn every 2 years, and the burn every 4 years, and the control not burn. So it's a randomized experiment because most of the experiments are randomized. So this is a randomized experiment. So, and in dry and wet area, so you can see the dry forest, wet forest is different. In the dry forest, the burning effect is very significant. Okay, but in the dry forest, it's not that significant. So that means because you don't, in dry forest, you don't have very thick leaf flow. Okay, next one, please. And of course, we're looking at the impact on different trees, not just on the look at the different tree species. Look at the biodiversity, how they respond. And the understanding is some species more sensitive to prescribed burning than the others. Okay. Next one, please. And the other one work which is out of that is when you burn too frequently, like burn every 2 years in the wet forest, you lose a lot of valuable organic carbon, nitrogen availability, and the to the extent its impact on the tree growth. So that means it's on biodiversity too, on the both bacterial and fungal biodiversity. Yeah, next one, please. And the carbon you lost tend to be high value, like water soluble, or easily usable by microbials. Okay, like a carbohydrate. Okay, and the next one, please. It's all work been published. So I'm not just because it got so many things. I don't want the world on one PhDs. The biological nitrogen fixation, and we also use natural abundance, but we also use labeling because natural abundance have some problem because sometimes if the variation of natural abundance of soil and air is not big, sometimes you have problem. And in this case, we have problem because the variability of soil delta M15 and tree uptake and air is very small. So we have to use M15 enrich to be able to see the nitrogen fixation capacity impact by the prescribed burning every 2 years, every 4 years, and control. Yeah, next one, please. So what we found, M15 enrichment is work, but it's very artificial because you introduce some species. So you tend to overestimate the biological nitrogen fixation capacity. Okay, but it does see the treatment difference. Okay, and when you burn very frequently, because you lose a lot of nitrogen, but not biological nitrogen fixation is increased because the symbiosis because between the rhizobia and the plants is working. When you got too much nitrogen available, and you fix nitrogen, it requires a lot of energy. You break the 3-bond nitrogen gas, you need 12 ATP. But when you go with water, it's much easier. So thermodynamics, energy conservation. So if you have a lot of nitrogen, they don't fix nitrogen. Okay, next one, please. And we're also doing the soil property, the top 30 centimeters. As expected, carbon is lost, many things lost, but so what? After the impact on tree growth, I said, is varied, but in the dry area, almost no impact. But on the wet area, different species, different. Next one, please. Okay. I would pass this one. The next one, please. Okay, in summary, these two experiments indicate you cannot burn too frequently. Okay. At least you should burn more, at least not less frequent than 4 years. If you burn every 4 years and the control looks like it not that much different. Okay, but you need to be varied from wet side, dry side. Okay. Yeah, next one, please. Let's try this destructive work, section 7. Well, the burning certainly impact on phosphorus, you know that because of the phosphorus variability will increase. It's useful for nitrogen fixation too. So it's also useful for seedling regenerate. The other thing for people not aware of Australia, eucalypt need fire to regenerate. So for ecology, for forest succession, forest is a must. So because they got a very hard the cover, the coal. Without a fire, they don't break. So the eucalypt cannot generate. So actually fire is the wildfire in Australia is quite common, like 50 years, 100 years. And the fire is also essential for acacia, understory acacia, because they also need the fire regenerate. So the fires is important part of ecology, but not too frequently. Okay, the recent climate change is leading to that the wildfire is become so frequent. Okay, and the flooding too, and drought. Next one. And we've done also microbiology work to collaborate with my Professor John Kenny in Western Sydney, and he is a very well-known ecologist. Okay, so we've done some work, and they indicated the fire has major impact on fungi hyphae, okay, which is published in the journals. So I'm not going to detail. The long term, if you're burning every 2 years, that has a devastating effect. So not too frequent burn. And generally wildfires is very rare. You have wildfires every 2 years. So wildfires much like longer. Sometimes, but it become frequent. Sometimes 5 to 10 years. Okay. Okay. Let's try this system. Yeah, it's working now. So we've done a lot of stable isotope, looking at the carbon-nitrogen cycles, and a lot of mycology research, molecular been done, and its impact on different fungi species vary too. I don't want to bore you on the detail because all the paper can be bound. Now, in summary, after all the work, fire work in controlled experiment, but in the last 20 years since I moved to Griffith University, so I also did this urban forest. So I follow up the field reduction burning, but not experiment, block by block, to understand the real fire impact, burn every 5 to 10 years, or sorry, about every 8 to 14 years at the frequency. And so many students have done the work, and I like to highlight, I think Fred also did some good work there, so published. And I like to acknowledge that they might all, from all aspects, from the ecophysiology, from microbial, fungi, bacterial, greenhouse gas, you almost, because on campus so easier. So we test every method there. So recently we have a trial they call natural abundance method, using the natural fractionation of M15 to fingerprinting every nitrogen cycling process. And we find extraordinary finding there. And that is leading to, we use tree to be able to detect the drought, the flood, because the drought in the past, people can find it through tree, but nobody else found flood. So we can detect flood using M15. Okay, and the fire, you can also detect fires using M15. You can see so by verifying that, you can go back to look at internationally, the global fire history, flood history, drought history in the last, say, before Industrial Revolution and in the last 150 years. And what we found is, I highlight that, the frequency, the intensity of both climate extremes, particularly flood, drought, and the fires, are increasing exponentially. And what that means, the wildfire is likely to be more often. And the last year, I don't know, people follow flood in Australia. In Brisbane, we have 3 floods. Each flood, according to history, is 25 years, 50 years. How come 3 floods in a year? You know, so it's not drought can killing the trees. In my backyard, the 3 floods killing trees too, because of the flood too long. Without oxygen, the trees also die, been choked to the death. So I think we need proactive to control the greenhouse, adapt greenhouse gas, reduce, mitigate greenhouse gas, because if we don't do that, the nature will do it, either through flood, through drought, through fire, through disease, through pest. So my suggestion is, as a scientist, we need to be positive. We need to start now doing something. So one of the things I'm particularly passionate for is biodiversity. The biodiversity, not just the natural forest biodiversity, but the biodiversity in landscape is paramount important to mitigate climate change, reduce the pest disease. The other one I'm very interested, but not as a carbon sequestration, is biochar. Because biochar, what we found, can regulate soil micro, help soil micro to recover. But you probably not use that as a recovery, but ecosystem recovery, microbial recovery, because biochar is a material can last very long time. So they can help microbial recovery. Once the microbial is healthier, so your plants will be healthier. Okay, but focus on economic crop, like horticulture crop. That means you're also making money out of that. And then a healthy product, fruit, and a healthy community. So I'd like to stop my talk and then happy to answer questions. Thank you very much.
So I'm just curious. I don't have a lot of experience with climate change, but between controlling for carbon loss and controlling for nitrous oxide, which one is more important for climate?
I'm sorry, I'm trying to put the plug in. Say again.
So between controlling for carbon loss to the atmosphere, carbon dioxide, and controlling for nitrous oxide, which is more important for climate change?
Very interesting questions. What we found recently, the carbon cycle is disrupted. Okay, it's not just nitrogen. Oh, sorry, nitrogen cycle is disrupted. It's not just carbon cycle disrupt. What we found, the N2O emission through denaturfication mainly is fast increasing. Partly is because increasing flood. Flood, because the denaturfication need a flood. And also drought. The climate changing, the feature of climate change, I forgot to mention that in addition to my experiment, there's an atmospheric modeling too, which is published in Science 2014. What the key results on the terrestrial ecosystem, land-based ecosystem, warmer and a drier future. So warmer and a drier. So that means that globally, most of land-based water is limiting, which is indicated by spring. But climate extremes, drought, that means you got a lot of nitrogen sitting there, not sit. On the land, not paddy fields, not rice system, not underwater. Oxidation is very dominant because most of agricultural land, forest land, degraded. The carbon is limited. The energy is limiting. Oxidation is high. So the nitrification, microbial, to survive, they need energy. They actually oxidize ammonium to nitrite to gain energy to survive. Of course, if you have a lot of carbon, water soluble, they don't need to do that. It's much easier. You soluble carbon than oxidation. So that indicates carbon reduction is lead to high oxidation state because the carbon is reduced. The more organic carbon, the more reduced environment. The carbon reduced, that means oxidation is increased. And also, warm, dry, that means the soil is dry. There's more oxygen in the soil. So oxidation is overwhelming dominant. So it means nitrification is a feature. And then you know that microbes, just like human beings, we don't like oxidized material. Okay, if you think about nitrite, just like burning the fires surrounding a campus or surrounding microbes, now human beings like fires, just burning them. Micro is the same. They like cool environment. So not if the micro is nitrogen deficient, they will take it because they build up body. But the rest nitrite denitrify. When the flood is coming, they send off as a gas. That means no more nitrite. The system become cooler because it's less oxidized. Okay, and because of lack of energy, lack of oxidation, most likely denitrification product is N2O, not nitrogen gas. So that means N2O is fast increasing. That's why in the last 60 years, the N2O is quadrupling. The first 40 years double from 100 ppb to about 200 ppb. The last 20 years double again from 200 ppb to about 396 ppb. If you follow the phenomenon which I say nitrogen going mad, next 10 years double, next 5 years double, that means in 15 years time, the N2O will be 4 times of current. It will be 1600 ppb. That means 1.6 ppm N2O. If you minus 400 currently, net increase is 1.2 ppm. But N2O warming capacity is 300 times CO2. That means in next 15 years, this if you follow the rules, the N2O warming capacity is going to exceed carbon dioxide, because by the middle of the century, the carbon dioxide concentration estimate about 600 ppm. Minus 280, that means 320. So you got a double warming. So I'm drawing carbon warming, but also nitrogen warming. So that is one reason it's become global boiling. The source is increasing, the sink is shrink. So I hope answer your question. Nitrogen cycle is disrupted.
Yeah.
It's not very positive.
It's not well discussed compared to carbon. That's why I'm asking.
Yeah.
Yeah. Okay, thank you.
We've been talking a lot in this conference sorry, about the importance to share our findings with the public and the decision makers. So I was wondering, regarding the work you've done in the urban forest, were you able to share this with the Brisbane Council, City Council?
Yep. One of the key findings I forgot to tell you, not the control experiment, but the monitoring last 12 or 16 years. The prescribed burning has little impact on the tree growth, on the soil carbon, on nitrogen stock. The only impact the prescribed burning is on the little floor. Okay, but little floor we want to control. What that means, the water soluble carbon, because the little floor it's a water soluble carbon, that's where wash is significantly reduced. What that means, biodiversity is implicated. So the biodiversity is changed. Okay, what that means, I think biodiversity probably is changing for worse, but I haven't found the indication what, like a nitrogen, for example, it's definitely generating more N2O. Okay, so what the impact? What I'm trying to say, I talked to the Brisbane City Council. Just tell them you have to burn it, and the current region about every 10 years. No impact on the carbon nitrogen cycle stock, but it does influence biodiversity. And then, but you have to do it because otherwise, wildfire, as I said, with the increasing drought, fuel, extreme heat, and the lightning. Actually, I forgot, even lightning. There's one nature paper say that once you got a lot of energy, and the climate change, lightning frequency is also increased. So you don't even to light fires. The nature will light fires. The chance will be significantly increased. Okay, so yes, we do. And in terms of farmers, for economic crop, you not just recover soil microbes, you actually improve the plant growth, plant health, and also the yield, and also food quality. you get a better economic outcome. So it's both ecosystem recovery, but also economically sustainable. And then you can recover the carbon cost. But we don't apply biochar uniformly. We apply biochar in the soil plant like a rhizosphere. So to amplify the microbes, rhizosphere effect, and the plant effect. So that means the biochar probably is a priming effect. It's probably not carbon sequestration. But once the microbial is stimulated, and the nutrient cycling is much vigorous. And then you get other benefits. So microbes is very important.
Thank you very much for this very interesting talk. And what you said about the end cycle for me was like, whoa, because you are talking that water cycle, well, disrupts or, well, interacts greatly with the nitrogen cycle.
Yep.
And I always, that I think about the nitrogen cycle, I think in fertilizers.
Yeah.
So thinking about this, if nitrogen is being depleted from soil,
yeah,
we are going to use more fertilizer.
We send them to air.
Yes, we are sending to air.
It's efficient. We lost.
Yeah. And then I think we are going to tend to use more fertilizers and to lose more nitrogen. And it is going to be a reversive cycle, isn't it?
Yes.
Oh my God.
Yes.
Yeah.
So we need looking at biological fertilizer, not chemical fertilizer.
Yeah.
Chemical fertilizer supplement, because the more chemical fertilizer you apply, the less fertilizer efficiency, because the microbial is degraded, the carbon is degraded, they don't hold. And the microbial is degraded, they oxidize ammonia into nitrate. And then when the flood coming, they send off to the air. And for sandy soil, they wash down. Ultimately to the river, they become air again. So it's either on-site denitrification or off-site denitrification. The end product is the same, most likely N2O. Because in water, the carbon is even more limiting, not enough energy. Reduction potential is okay in water, but energy is, so thermodynamics, energy conservation, energy balance is paramount important. So we got to think about energy. Every process is driven by energy in the nature. So it's energy process driving. So, and also thermodynamic second rule, they always going for the less orderly. Okay, that means more chaotic. Like, for example, from liquid to gas, from ice to water. So that is more natural, but to go back is the wrong way. It's anti-thermodynamics.
Yeah. Thank you very much. Final question? Oh, well,
that's
okay.
I hope my English is understandable. Okay.
Yeah, thank you very much. You have been now talking a lot about the forest ecosystems and saying that they have already surpassed the...
Is because that tree ring, I can look at real climate change. But I'm doing agriculture too.
I'm sorry, I'm moving, so we don't give our backs to these people. No?
Okay.
Yeah, my question is, at the end of your talk, you said something about biochar. So biochar is applied to agricultural land.
Yes.
But we're talking about the forests.
It's also burning. Your fuel reduction, you get biochar too.
So you are proposing to add biochar to the forest?
No, but just they do impact on cycle, nitrogen cycle.
Yeah.
Similar way like carbon.
So if we want to, like, at least control these trends that you are talking about.
Yeah.
One, just tell me if I got you right, no? Or just I ask you to say more about it. So in the agricultural systems, we should, as you right now said, increase the carbon so that it's not energy limited, at the same time add more organic nitrogen.
Restore carbon.
So then there, the program should go into like adding biochar mixed with.
Not biochar. Biochar in small amount, not carbon sequestration. Priming effect, like a
So you
naturally stimulate the micro.
You have for sure mixed it with some more labile or organic matter.
Yes.
I guess.
Yeah.
No?
Yeah.
And then for the forests, are you there proposing some different kind of forest management to? Can you please go a bit?
Well, the forest first don't cut forest, because you cut forest, you even get big thing.
Well, what we are seeing now is that the forests are dying.
The forest, you need to think about biodiversity. You manage it forest in a biodiversity way. Means either mixed forest plantation rather than single plantation, mixed species plantation, because that's more. What I'm saying, it's better coping with extreme weather, climate change, because of the complement. Okay, complementation. I think in ecology, there's two theories. One is Darwinism, is a selection. One is neutral theory. Okay, and personally, from the work I'm doing, I incline to think about is selection. So you need to have different species. They have different functions. And they are there for good reason. It's not just by chance. They are complementary. So biodiversity in soil, biodiversity in forest. If you cannot do the mixed plantation, you should think about keep some natural forest as a biodiversity reserve, because that is potentially bugs. A lot of things come from there. They actually can this is a climate change. Okay, for example, if disease coming, there probably is a potential control, using biocontrol rather than chemical control. So that is biodiversity. The other biodiversity is landscape. You're planting, there's one paper published in Nature, is rubber plantations. In rubber plantation, everything is bad. But the experiment is they keep natural forest reserve in a pocket. In a harmonic or zag way, that's sustainable. So biodiversity can be different format. It doesn't need to be mixed. But microbial biodiversity, you need to start now, because the biodiversity in the soil is going the wrong way.
We agree on that.
Because lack of carbon and the intensive chemical fertilization and so on.
Yeah, thank you very much.
Ya pregunté y tenemos más tiempo para preguntas.
I think Faith got questions. Huh?
Thank you, Dulce. Thank you for your talk. I have a question. I have read that if the soil in the forest has a high concentration of nitrogen, the diversity of the forest is reduced. Which one is the reason for that?
Say again.
If the nitrogen in the soil is high, the concentration is too high.
No.
The diversity of the forest is reduced. Why?
Now,
what is the reason for that?
Well, I probably haven't explained myself very clearly. Not agriculture, because agriculture, of course, you apply fertilizer. But in forest, nitrogen availability is declining. It's because denitrification, flood washing, declining. Okay, denitrification, you send about 100 kilogram nitrate into the air, with almost every 50 to 100 kilograms to air every single flat. Plus you wash away a lot of soluble carbon nitrogen, because water-soluble carbon nitrogen are the most important carbon and the nitrogen, readily accessible by microbes. If you lose that, it's influence microbial diversity. For example, if you lose that carbon, your nitrification is increased. Nitrification in the ecosystem generally is bad, oxidized. Once you become nitrite, it's like, so you put fire in the soil, it's hot. The microbe doesn't like it. They like a cool environment. Okay, so when water is coming, nitrite probably don't, nitrify probably wouldn't mind because nitrify like oxygen, but denitrify just hide nitrite. Okay, they just, because what I found, denitrifier, if you air dry, you don't need even to burn. If you air dry them for a couple of days, just like in the lab, not oven dry, they can lose about 75% in 2 or 3 days, the function. So denitrify, which is like reducing environment. Oxidizing environment is not good for denitrify. But denitrify is very powerful everywhere, so global. So that's why we can use tree ring to fight flood, because flood is so frequent, you actually can see it in the tree rings. Yeah.
Bueno, si no hay más preguntas.
No.
So, for the questions. Vamos a entregarle sus presentes de parte del gobierno del estado de Chihuahua.
Thank you very much. Very much. Thanks. And thanks, sorry, I really like to thank all the organizers. That's it. On a very short notice, still managing. It's about
a la revista siguiendo siguiendo las instrucciones para autores y ya que se siguen esas instrucciones para autores en una de las secciones cuando requiere additional information, les pregunta si esto pertenece a un special issue y pues le ponemos que sí y le ponemos este special issue de Soil Sustainability and Innovation para contar con sus valiosas contribuciones. No sé si Fabián tenga algo más que agregar. Muy bien.
Está casi al final. Primero tienen que subir su contribución y casi en el último paso, en la última ventana, es donde les pregunta o les pide que marquen si esa contribución forma parte de un special issue. Porque en algunos casos para seleccionar el special issue es casi en la primera ventana, ¿no? Entonces, en este caso es en la penúltima, ya casi cuando le dan enviar, ahí les dice que si es una contribución regular o si forma parte de un special issue, y bueno, pues ya ahí le ponen que es del special issue. Y bueno, no se cobra nada, no hay APC o cuota por publicación. Entonces, pues esa es una gran ventaja, ¿no? Y tiene factor de impacto, es de Springer. Hishu es el editor en jefe de esa revista y bueno, entonces ojalá recibamos sus contribuciones. Hasta el momento hemos recibido 28 contribuciones, pero bueno, es un buen número, pero también muchos de ellos pues ya han sido rechazados desafortunadamente y bueno, esperemos que recibir más para que quede un buen número de artículos. Ayer me decía el editor en jefe que bueno, espera que se junten unos 20 contribuciones aceptadas. ¿Sí? Entonces, bueno, esperamos sus contribuciones y muchas gracias. Es todo.
Y ahora ya anuncias del Congreso.
Bueno, pues agradecemos al nuestro conferencista magistral y pues vamos a dar inicio ya con las recorridos de campo. Entonces, por favor, les pedimos que ya empecemos a subir a los